All right. Our next speaker is Lukas Stennis. He's a PhD student at the Ruhr University in Bochum. His research focuses on cryptanalysis, and he was also part of the team that uncovered a vulnerability or a weakness in GPRS. And as a matter of fact, he got a Best Paper award for the research he's going to present here. So that's sort of quality controlled. Lukas will speak about breaking NATO radio encryption and present an attack on the used encryption algorithm that is used by the US military and the NATO for high frequency radio. Please welcome him with a huge round of applause.
NATO and US military use an insecure encryption algorithm called half-loop 24. In this talk, I will explain how you can break it. Okay, but let's start in the very beginning. Let's start by explaining what symmetric cryptography actually is. And for this, we need our two main characters, Alice and Benjamin. Okay, so you got the joke. Usually in crypto, we call Benjamin not Benjamin, but Bob. But as I'm using elephants to explain cryptography, I call it Benjamin, or call him Benjamin. And if you're wondering why I use elephants, this is because those are actually not simple elephants, but CASA funds. And CASA funds are the mascots of CASA, and CASA stands for Cybersecurity in the Age of Large-Scale Adversaries, and is the cluster of excellence at Ruhr University for the studies of cybersecurity. And now Alice and Benjamin want to communicate over an insecure channel. And the problem is that there's a third party, an evil party, namely Charlie. And Charlie wants to, or is eavesdropping on Alice and Benjamin. And now what Alice and Benjamin, of course they don't want Charlie to eavesdrop on them. And so, in a metaphor, what they can do, they can put the message in a very, very strong box. So the box must be so strong that Charlie cannot break it. And then they put a padlock on the box. Again, the padlock must be so strong that no one, so also not Charlie, can break it. And then they can send the box around, and both of them have a key to open and close the padlock. And then they can communicate, but Charlie cannot eavesdrop on them. And that's essentially what we want to achieve also in the digital world by using symmetric cryptography. And if you're wondering why it's called symmetric cryptography, it's because the key on both sides is the same. And of course, if there's symmetric cryptography, there's also asymmetric cryptography, also sometimes called public key cryptography. And in the same notion, symmetric cryptography is then called secret key cryptography. But roughly speaking, you use public key crypto to establish this key on both sides, and then you use symmetric crypto to do the actual encryption. Okay, and of course, encryption is used nearly everywhere, right? On your phone, if you're writing a message on Signal or something, you use encryption, of course. But another very prominent example is HTTPS, so TLS, right? If you go to a website, you have this padlock again in the browser bar, and if you click on it, you can look at the details, and then here it says something like the information about the encryption, TLS, AES, and so on and so on. And what we are interested for, most for symmetric crypto is AES, because AES is a block cipher, and it's not just any random block cipher, but it's the block cipher. Yeah? AES is the advanced encryption standard. It's probably one of the most used crypto algorithms in the world. And essentially what AES does is it takes an input, 128-bit input, so this input we usually call the plain text, and then it will generate a ciphertext, which again is 128-bit, and it does so by taking another input, namely the key. And now, essentially, the security guarantee that AES gives us is that if the attacker, so Charlie, has no knowledge about the secret key, then there's absolutely no way that Charlie can turn this ciphertext back into the plain text. Yeah? And that's, of course, already very useful, but okay, in the real world, of course, we want to encrypt more than just one block, and then we need some we call it mode of operation to specify how we deal with multiple blocks. And like I said, AES is the advanced encryption standard, so it's a standard. It's was specified in the early 2000s by NIST, so it's a US standard, and since then, it's widely used. And so, like I said, essentially the security guarantee is that no one can decrypt the ciphertext without a key, and now you might wonder, okay, but why? So why are we so sure that no one can do this? And essentially, because no one found an attack yet. Yeah? So there's not really like a proof, a mathematical proof that you can say that AES is secure, but for all the attacks that we know that AES is resistant, and that's why we trust so much in AES, because it has survived more than 2 decades of research into it. Okay, but unfortunately, even though AES is such a super cool cipher, we don't have the time here today to look into all the details, but if you want to know more about it, of course there's the lecture by Christoph Paar online on YouTube, so everyone can watch it just for free. Christoph is a professor in Bochum, and essentially this introduction to cryptography lecture is the lecture you would attend if you study cybersecurity in Bochum. And just a side note, Christoph by now is the founding director of the Max Planck Institute in Bochum, so his lectures are super nice. Okay, so that was a short introduction to symmetric crypto, but okay, I guess you're not here to get an introduction to symmetric crypto, but you're here for the military radio, right? So let's start going into this military radio, and let's do so, or let me do this by showing you this picture, and now giving you some seconds to guess what the connection of this picture and this talk actually is, so the military radio. And actually, there's no real connection. The only connection is myself, because I took this picture 2.5 years ago, roughly, in Athens. And I was in Athens for my very first academic conference. It was FSE, so FSE stands for Fast Software Encryption, which is the name of the conference to be in symmetric crypto. And during the time it took place, there was also the national holiday of Greece, and then they celebrate this by putting tanks in the street and fighter jets in the air, and everything was a bit crazy, but that's where I took this picture. Okay, and actually at this conference, I attended a talk which was titled Cryptanalysis of the SODAC Cipher for HF Radio Automatic Link Establishment. And this one caught my attention, and I want to briefly explain this title. It was given by Markus Dansari, who later also worked with us on breaking half-loop. But the title, cryptanalysis, that's just the word that you use if you look into a cipher and try to break it or show its security. And then this SODAC cipher, SODAC is just a name, and then cipher, well, it's a cipher. But I want to talk a bit about HF radio and automatic link establishment. Okay, so first, HF radio. HF radio is, HF is just high frequency, so the idea is that you use a high frequency, so it's a frequency between 3 megahertz and 30 megahertz, because then there will be an effect called skywave propagation, which, essentially what's happening is that your radio signal is reflected by some particles in the upper atmosphere, and then it will bounce back to the Earth, and then, it can even go on and bounce around, and thereby it will travel a very, very large distance. And so, because of this, it enables also communication across very large distance, and without the need for any infrastructure. So you don't need satellites, you don't need cell towers, you don't need anything, essentially. You only need radios on both sides. And, who is interested in such technology? Of course, the military. Also others, like diplomatic service or disaster management agency. Yeah, it's pretty clear if there's let's say, big earthquake or something that destroys all cell towers, then you want communication that doesn't need any infrastructure. So that's very helpful there. And then inside this HF radio, SODAC, so that's the cipher that Markus analyzed, and then the replacement half loop is used for encrypting handshake messages, and thereby it's they try to use it to ensure confidentiality and authentication. Okay, so let's talk about automatic link establishment, because as you might guess, HF radio is not that simple, right? It's not just, okay, you send a signal and there it is. but actually it's very complicated. And up to the mid-80s, you needed very skilled operators on both sides to establish this communication link. And to make this more easy, they came up with this automatic link establishment protocol, ALE for short. And there, of course, we are not going into the real details, we are simplifying a lot, but essentially what's happening is that you have a three-way handshake in the beginning, so that it's very common in communication. So Alice essentially sends a message saying, "Hi, I'm Alice, I want to talk to Bob," and then Bob will reply with a similar message just saying, "Okay, I'm Bob, I also want to communicate with Alice." And then Alice will again send a message saying, "Hi, I'm Alice, I want to communicate with you, Bob." And then again, simplifying a lot, but then the link is established and the actually communication, so that's either voice, so voice chat, or data. So for example, you can use HF radio to send emails or whatnot, goes on, and in the end there's a finished message. So Alice will just say, "Okay, I want to stop the communication here." And then, as you might notice, we have this padlock here, and this is because those messages, this handshake messages, and then the finished message are encrypted using, in either SODAC or half-loop. So SODAC is the predecessor of half-loop, so it was used until 2017 probably, but now you use half-loop to encrypt these messages. And now, why do you need encryption here? So by encrypting those handshake messages here, if you use strong encryption, you get some nice properties. First, the confidentiality of the handshake messages, which means that no one that doesn't have the key knows who is communicating, right? Because I said the message contains the identity of Alice and Bob. So if you would not encrypt them, everyone would see, okay, it's Alice and Bob communicating. And of course, I say Bob, but we said it's Benjamin in the beginning, but okay, don't worry. And then the second thing, or security goal that you get, is the authentication, right? So if Alice and Bob are using this secret key that only they know, then if they decrypt a message and it says, "Hi, I'm Alice," then Benjamin can be sure that it was actually Alice sending this message. And this is somehow kind of important for HF radio, because when you establish the link, you cannot just listen to others and then establish a link to someone else, right? So this authentication also ensures availability. Yeah? So of course, anyone with a very powerful sender can just jam the radio frequency so that Alice and Bob or Alice and Benjamin cannot communicate. But if you have the key, you can just send a message or the 3 messages in the handshake and then establish the link, and then Benjamin cannot establish a link with Alice anymore. So that's also something why you need the encryption there. And then lastly on the slide, I want to point out that half-loop, so the cipher that we are going to attack in just a minute, is used in the handshake messages and finished message only, right? So what I will explain does not apply to the actual voice or data that is sent. So it's in the handshake messages. Okay, so let's go into the details of half-loop 24, so the algorithm that we attacked. And half-loop is actually specified in some military standard. And if you know anything about FIPS 197, so that's the standardization document for AES, then this might look familiar. Yeah? So we have some steps here: the sub-bytes, rotate rows, mix columns, and add round key. Those are very similar to AES, and that's because half-loop is very similar to AES. And if you wonder whether this document is secret or anything, no, it's not. It's public. Yeah? So actually, I said before, I was in Athens, and then Markus gave this talk about the predecessor of half-loop. And in the end, he said that now there's this half-loop cipher which is being used. And then I asked, okay, but is it actually public? And he said, yes, you can just Google for it. And then you find the website of the Department of Defense, and there you can download this PDF. You just have to scroll down, I don't know, like 300 pages to Appendix G, and there you find the specification of half-loop. Okay. So let me give you some details. And actually, I should say that there are 3 versions of half-loop: half-loop 24, 48, and 96. And we are looking into 24. and this number is the block size. Yeah? So remember for AES we had this plaintext and ciphertext, they were 128 bits, and for half loop they are either 24, 48 or 96 bits, and we are looking into the smallest version, and for this talk are ignoring the other two versions. So half loop is a tweakable block cipher, and on the slide I call it E so that I don't have to write half loop in this small box. And like I said, it supersedes the SODAC cipher, and one side note about SODAC, it only used 56-bit keys. And if you know anything about cryptography, 56-bit, the key length, is also what was used for DES, and that's simply not enough. So that's something that you can easily brute force if you really want to do. So actually on first glance, it's good that since 2017, half loop is specified in this military standard, because it has a 128-bit key. Yeah? So here in the picture on the right, you see that we have the 24-bit plaintext, 24-bit ciphertext, and then a 128-bit key. But in contrast to AES, we have this additional input, and it's called T here, and T is a tweak. And the tweak consists of the current time, a word counter, and the used frequency of the radio signals. And we will talk about this a bit more in just a minute, so what this tweak is, why we need it, and that it's actually a nice idea to have a tweak. And then, like I also said briefly before, half loop is very, very much inspired by AES, which of course, at first glance, is a good thing, but as we will see, the details matter a lot. And yeah, so why is it so, or why can we say it's heavily inspired by AES? Because it reuses many components. Yeah? So in just a minute we will look into even more details of half loop, and we will see that the S box, so that stands for substitution box and is a central part of a block cipher usually, and they just took the same as in AES, which makes a lot of sense because AES uses a very strong S box. And they also use essentially the same key schedule. So if you don't know what this key schedule is, don't worry, we will come to this in just a minute. And also the state, for AES we have a 16-byte state, so 128 bits, and we usually write it as a 4x4 matrix. And for half loop, we essentially shrink down this matrix to a 3x1 matrix, and then each entry in the matrix is 1 byte, so an element in F2 to the 8. And the same for AES, we use 10 rounds, so whatever a round is. So, okay, now we have this. I want to give you some more details about this tweak. So why do we need it? Why do we want a tweakable block cipher? And for this, let's look at this famous ECB tax. Yeah? So what happens if we encrypt an image in ECB, in electronic code boot mode? Because if you remember, I said that something like AES or any other block cipher only encrypts 1 block per time, right? But usually an image is more than 1 block. Yeah? And maybe for the sake of the example, let's just assume that 1 block always is 1 pixel. Yeah? And what happens if we encrypt every pixel with AES and the same key without any connections between the blocks essentially? So then we call it electronic code boot, or in short ECB. And then the ciphertext looks a bit like this. And of course that's not a secure encryption, right? Because secure encryption means that you don't see any information about the plaintext, but here it's pretty clear that you can easily recognize that this is the tax. And now, usually you would use some mode of operation like GCM, for example. In the example we had with HTTPS, you had GCM. But if you have a tweakable block cipher, so you have this additional input, actually you can use ECB, and that's nice because ECB is very simple. Yeah? And if you use a block cipher, a tweakable block cipher with ECB, then you get what you want. Yeah? You get just some noise and you don't see any information. And the idea is that the tweak is an additional input that changes, even though the plaintext doesn't change. So here we have maybe a white pixel and then another white pixel, and then we get the same ciphertext here. But now, for example, if we take the position of the pixel, so the XY coordinate, as an additional input and feed it to the tweakable block cipher, then the ciphertext will change, although the plaintext was the same. And then we get something nice and secure again. Okay, so that's for the tweak. And maybe to say, of course, you also should use some other, like a counter, so that if you encrypt different images, you have the same position, it also changes, but okay, that's just a side note. Okay, so let's go into even more details and let's get a bit technical and look into the round function of half loop 24. Yeah, so these are the operations that are essentially happening over and over again, so 10 times in half loop. You apply these operations and then you have the ciphertext. So at the left side, the input, you have the plain text or the current state if it's not the first round. And those are 24 bits and you divide it into 3 bytes, so 3 times 8 bits. And then the first step is the round key addition. So the round key is something that we derive from the 128-bit master key, and then we add it, and when I say add, I mean we XOR it, so the XOR, the exclusive OR. So we do it on every bit. If the bits are the same, we get a 0 output. If the bits are different, so the state bit and the round key bit are different, we get a 1 output here. And then the next step is the S-box, and I told you before, this is just the AES S-box, and then, I mean, if you implement it, it's just a lookup table. Yeah? So you have the input X, so that's 8-bit, so there are 256 possibilities, and then you just have the output value in a table. And then for the security, it matters a lot how this table looks, but okay, for us, it doesn't matter too much here. Yeah? And then the next step is the linear layer, and it's composed of actually 2 subparts. You have this rotate row, so which just does a bit rotation on each byte, and then this mixed column, but because it's linear, yeah, and you can see I put this box here, you can just think about this step as a multiplication with this binary 24 by 24 matrix. Yeah, and then, because I mean we are doing computation on bits, so binary, it means that the additions are again XORs, or I mean equivalently you can say that you reduce modulo 2. Yeah? So in the end, of course, for every bit you again have 0 or 1. Yeah? So 24-bit output again. Maybe let's do a quick example. Yeah? So let's say our input is 01, 02, and 03, all in hex. Yeah? So 0 is 4 0 bits, 1 is 3 0 bits, and then 1 bit set. And then we have some round key, and then the first step is the round key addition, and then this would be the output of the round key addition. Yeah? So if we have 7F and 01, we flip the least significant bit of the F, and then it's get a E. Yeah? And now you can see I put, of course, not all the 256 values of the S-box here on the slide, but 7E I put, and then you do the lookup. Okay, input is 7E, then the output is F3. So actually also quite simple. And then for the linear layer, it's maybe a bit less clear, but just trust me, you essentially do this this multiplication with the binary matrix, and then this is the output. Yeah? So if we do the intermediate steps, you can see here the rotation, and then the mixed column. Yeah? Mixed column is also an operation in AES. So then you get this output. Okay. And now, like I said, for a half loop, we have 10 rounds. So essentially, you just do 10 times this round function. So yeah, this is the first round function, taking round key 0, then doing the S-box, the linear layer, and then you are in the next round function. So you add, you add round key 1, do the S-box, the linear layer, and so on and so on. And yeah, you do this 10 times, but actually the last one is a bit different because there the linear layer would not add any more security, so you can just leave it out. But you do another key addition, because otherwise an adversary could just compute back. So you need a key addition in the very end. And that's all of half loop. Yeah, that's the complete algorithm. You put in the plain text on the left, you do your 10 rounds, and then you have your ciphertext. But of course, there's one thing missing, because I didn't explain how you actually get these round keys, right? So of course you have this master key, but how do you get round keys? And for this, we use the key schedule. So the key schedule again is borrowed from AES with a minor exception, or I mean, let's say 2 minor exceptions. First, we need way less round key material, so it's a bit shorter. And second, we have this tweak, which is XORed in the very beginning. So we split the key into 2 parts. So 64-bit, first 64-bit, and the remaining 64-bit. And for the first 64-bit, we add a tweak T. So this is the used frequency, timestamp, and the word counter essentially. And we XOR this to the first bits of the key, and then we do this AES key schedule. And then the AES key schedule is quite simple. We just have this XORs on 32-bit words. And yeah, it's a FISO-like network. And you have this function G. We actually don't have to worry about it, but yeah, there are just some more S-boxes and some shuffling going on in this G function. And then how you get the round keys? Well, you just take the first 24-bit for round key 0, next 24 bits for round key 1, and so on and so on. And then you only have 1 byte left. Then you do this AS round key, a key schedule function, and then you have this new state, and there you just take the bits that you just continue taking the bits, and then you already are nearly there. You have 2 bytes of round key 10, so that's the last round key you need. So you just need 1 more byte, and that means that you apply this function again, but okay, you can throw away everything except for the first byte. And then we have all the 264, so that's 24 times 11 round key bits that we need. Okay, so now that we know how half loop works, let's look into the attack finally. And the attack I'm going to show you is based on 2 papers. So the first paper is Breaking Half Loop 24. It was joint work with Marcos Danzari, who presented his work on SODAC, so the predecessor, which caught our attention then, and Patrick Derbez from France, and Gregor Leander, who is my supervisor in Bochum. And in this paper, essentially, we said, or the outcome of the paper essentially was, okay, half loop 24 is not secure. Yeah? We have an attack, and it's actually a quite strong attack for, let's say, the theoretical standards, because we said, okay, we can break it if we have, if you can eavesdrop for just 500 years. And then, I mean, in theory, that's a very strong break, but okay, in practice, maybe you don't care if the attacker needs 500 years worth of communication data. But then I presented this paper in Kobe in Japan last year at FSE, so the Fast Software Encryption conference, and then a colleague of mine, Sharam, who by now also is back in Bochum, but back then was in Nijmegen in the Netherlands, came to us and said, okay, I think we can improve the attack, and then we again put some time in it, and actually we then realized, we can improve it massively. And then, of course, because we're in academia, we wrote again a paper about it. And then, I presented this at FSA this year in Leuven, and we actually got a best paper awarded, which was, of course, super nice for us. Okay, and so before we go into the details, I want to point out that at first glance, attacks in cryptography might be a bit strange, because the attackers are super powerful. Yeah? So for an attack, usually, if you have the attacker, Charlie, on the left and Alice on the right, and then Alice, of course, has a secret key, Charlie can make queries to Alice. So Charlie can say, okay, Alice, please encrypt this plaintext for me. And then Alice will do so, which is a bit strange, because in practice, hopefully it's not like this. Charlie can not just go to Alice and say, hey, maybe you can encrypt this for me. But it gets even more crazy, because Charlie can also ask for decryptions. So Charlie can just say, okay, decrypt the ciphertext C prime for me, and then Alice will happily answer with P prime, so the plaintext corresponding to the ciphertext. And then this will go on, and in the end, maybe Charlie is supposed to come up with the secret key. Actually, in real cryptography, maybe let's say we are even more crazy, and Charlie just needs to distinguish whether Alice was really using the proper cipher or something just purely random. But for us, let's assume Charlie is supposed to come up with the key. Now you might wonder, okay, why are the attackers so strong? And this is because, if you know that a cipher is secure against so strong attackers, then you can be very confident in the cipher. And there have been many examples where, of course, you didn't intend to have such channels. So like Charlie can ask for encryptions or decryptions, but it happens that you don't intend to do it, but maybe you have something like, for example, in Bleichenbacher attacks where you can notice whether the decryption or the first bits of the decryption correspond to some specific value. But if you have security against such attackers, then okay, you're good. Okay, and the last missing piece is differential cryptanalysis. And of course, we are not going into all the details of this very fundamental technique in symmetric cryptography, which was invented by Biam and Shamir in early 90s. And by the way, this Shamir, you might know this name because it's the same as in Shamir's secret sharing or in RSA. So the S in RSA is also Shamir. So Shamir was super active, super strong cryptographer. And they came also up with this differential cryptanalysis. And there the idea is that you not only look at one plaintext ciphertext pair, but you look at another plaintext. And this plaintext P here, I already hinted it, P XOR delta, you have some specific difference. Yeah? So you have two plain texts, and then they differ by difference delta. And here I use the lowercase delta for the specific value of the difference. And in general, we will use the uppercase delta, yeah? So this little triangle that's an uppercase delta, to indicate that we want to talk about the difference. In this case, yeah, delta P is the difference between P and P XOR delta. And then because it's XOR, so we do this P XOR delta, and then the P will just cancel out, and then the difference is lowercase delta. And the idea of differential cryptanalysis is to use a very specific difference at the input, and then hope that if you inspect the ciphertext, or the difference of the ciphertext, you can learn something. Yeah? And notation-wise, we will not put both encryption ones here on the slides, but only one, and then we will put just the difference that we care about. And actually, you don't need to do this analysis for all of the cipher, but usually it suffices to only do it for parts of the cipher. Okay, now we have all we need, and we can look into the actual attack. So we get even more technical. So this picture you already know, it's the key schedule again. And now, of course, in Half-Loop, we not only have the plaintext as an input, but also the tweak as an input. And for now, let's just assume that the attacker can also control this tweak. That's not the case really in practice, but first we assume we can just freely control it, and then we will have a look how we can accomplish this in practice in the real world. Now what we are going to do is we are going to put a difference in the tweak. Yeah? So here we have the difference delta in the third byte. So yeah, the tweak is 64 bits, and everything except the third byte is 0, the difference. Only in the third byte you have the 1 byte difference delta. So that means we are encrypting two plain texts, and the tweaks are the same, except in the third byte they differ. Yeah? And now we are interested in what will happen for the round keys. And this is actually rather simple. Yeah? If there's a difference in the third byte, then there will be a difference in the third byte of the first round key. So round key 0 is the same, except for the third byte, there we have the difference delta. And for all the other round key bits here in the first row, nothing happens, yeah? Because the only difference is in the third byte. But then we are applying this key schedule, or the round function of the key schedule, and then because it's XOR, it will just propagate through. So we have the delta here, and then we will have the delta here. So that means no difference in those round keys, but in the first byte of round key 6, there again is a difference. Yeah? That means if you are encrypting P and P prime with those two tweaks, then the round key that we use so round key 6 will differ for both runs in the very first byte. And then, here the delta will also propagate this way, and that means that we also have 1 byte difference in round key 7, in round key 8, and in round key 9. Yeah? Now and maybe if you're wondering, this delta doesn't have any influence onto this byte, so it just stays the same. Now let's plug this in again into the full picture of Half-Loop. And in red here, yeah, you have the round keys that differ if we are doing these two encryption runs. And you can even put the specific positions. Yeah? So you introduce a difference delta here, 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 and here. And now the crucial step of the attack is that we can use a plaintext or a plaintext pair which has a difference which matches the difference in this tweak. Yeah? So we use a plaintext which is the same in the first 2 bytes, and then again has difference delta, and delta is just any value, any 1 byte, of course non-zero, but except that, any byte, and then they will cancel out, and we will have a state difference, so capital delta 0. Yeah? That means that when we do the encryption after the first round key addition, although we are encrypting two different plaintexts with two different tweaks, after the first round key additions, they are the same. And now if we have the same input to the S-box, and then the output of the S-boxes will be the same. Of course, if you have the same input for the linear layer, also the output of the linear layer is the same. And then if we have the same input into the key addition with the same round key, also again, the output is the same. And then this goes on and on and on until we add round key 6, only then it will start to differ. That means that the first 6 rounds, all those 6 rounds, we can essentially skip for free. Yeah, so we have this algorithm, Half-Loop 24, with 10 rounds, and 6 of the 10 rounds in the differential attack we can just skip. And of course, that's not good. Yeah? So we only have to attack the remaining 4 rounds. And If you just look at them, so we just zoomed into the last 4 rounds, we know that when we are encrypting those 2 plaintext with 2 different tweaks, with the specific inputs, we know that here the states, there won't be any difference in the states, so we have difference 0, and then we are introducing those difference with the round keys, and then this very last difference here, and then here on the right we will have the ciphertext. Now actually what we can do, because we can swap the linear layer and the round key addition, so we can just think about adding applying the inverse of the linear layer to the round key and then applying this here, and then we just have the difference here. And now we can just count, so how many information, how many bits of the key do we need to know to compute the ciphertext back to learn this difference? And well, clearly we need round key 10 and round key 9, also round key 8. But then here for the inverse of round key, or applying the inverse of the linear layer to round key 7, we actually only need the first byte of the round key to learn this difference here. And then how many bits are those? Well, that's 3 bytes here, another 3 here, another 3 here, and then 1 here. So in total that's 10 bytes, and 10 bytes are 80 bits. And 80 bits, okay, that's a lot if you want to run a brute force attack on those 80 bits, but that's way less than 128 bits. So that's actually already gives an attack that breaks half loop, at least in theory. So the attack would be just guess all of this key material, all of this 80 bits. And whenever in symmetric crypto we say guess, we just mean have a big for loop that tries all possibilities for this. And then you would compute the ciphertext back, check if you have this difference 0 here, and if indeed you have difference 0, then the key is a candidate that you have to check further, and if not, you can throw away the key. You know those 80 bits are not the real key that you need. And then you would do this for multiple pairs of plaintext and ciphertext, and eventually you will have the correct value for this 80-bit key. So there's a trivial attack in 2 to the 80 with 6 queries. So queries are again the messages that Charlie has to send to Alice, so the plaintext ciphertext values. And actually this is optimal. I'm not going into the details, but it's rather easy to show that even a brute force attack, so where you just assume that you can do as many computations as you want, cannot work with just 5 queries, because then there are just too many possible keys that remain. So you need 6 queries. But 2 to the 80 is a bit, it's quite a lot. So it's roughly in the ballpark of what the Bitcoin network is doing every day. So that's nothing that we can do on our computer in university. But we can improve the attack. So there you can do some pre-computation. And then essentially you only have to iterate all possibilities for round key 10 and round key 9, and then you have a pre-computed lookup table, and then you do a lookup, and then you see whether the key can work or not. And then you can even improve it a bit further. If you allow 2 more queries, then you only need 2 to the 48. And 2 to the 48, that's something that we can run easily. So we implemented the attacks. So the attacks I just explained are essentially those 2. So you need encryption queries, so you can ask Alice to encrypt something, but you do not need to ask Alice to decrypt something for you. If you have this, then actually there's a way more effective attack, so the time complexity, so that's essentially how many encryptions or decryptions you have to compute yourself, would only be 2 to the 10, so that's 2 to the 10 is 1024, so that's very, very simple, but you also need more queries, and also decryption queries, so that's bit unrealistic in this setting. But this setting, where we need a 256 or 2 to the 48 with 5 gigabytes of memory, of course 5 gigabytes, it's nothing, that's easy. Those we can actually turn into a practical attack. And then the setting is nothing theoretical anymore, but ALE, so this automatic link establishment protocol. We again need this 2 to the 48, so that's this attack. And then this 8 theoretical queries, if you can just ask Alice to encrypt something for us, translate to 2 hours of eavesdropping on Alice and Benjamin. So I will explain next how this works. But actually, let me point out, this 2 hours, you also need the plaintext. So you not only need to intercept the radio signals, but you essentially have to eavesdrop on a specific site. So you need to know what the plaintext are of the communication. Okay. So let's look at the attack in practice. And for this, First, we need to understand that in ALE, actually it's not only two parties that can communicate, but it's a whole network. And all of the network will share one symmetric key. Yeah? So there are a bunch of people and they all know the same key. And then, I mean, usually we called the communicating parties Alice and Benjamin or Bob. But in this case, Alice actually, I mean, there are so-called call signs. Yeah? So Alice might be called AAA. So these call signs, you can think of it as in the same way as a short phone number maybe, and it consists of just 3 letters. Yeah? So maybe we have AAA. And now what we are going to do, we are going to zoom into this 3-way handshake, into actually the first message of the handshake that Alice sends to Benjamin. Yeah? So we have Alice and Benjamin, but now Alice is called AAA and Benjamin is called AAQ. And the first message that, well, AAA sends to AAQ is, well, it says that it's sending the message to AAQ, and then it repeats that the message is sent to AAQ, and then the last word of the first message is that this is AAA. Yeah? So AAQ and AAA are these 3-letter call signs, and each letter is 7 bits, so these are 21 bits. So there are 3 bits remaining, and those are used to encode this true and this is. Yeah? And then, as you might remember, we have this tweak. So the tweak T consists of 64 bits, and in the 64 bits, we encode the time, a word counter, and the used frequency. We assume that the used frequency is constant, and the time, well, it's just the time, and then the word counter counts here. Yeah? So for the first word, you have word counter 1. For the second 24-bit word, you have word counter 2, and of course it's binary here. And then for the third word, you have counter value 3, so 1, 1. And now we just assume that some time passes, and eventually AAQ, so yeah, Benjamin, will essentially send the same message, because AAQ also wants to communicate with AAA, or wants to establish a link sometime later. And then the messages will just be mirrored, right? So we have 2AA, 2AA, this is AAQ. And now, what we're interested in, what was this delta before, is exactly here. Yeah? So we see that the plain text is actually all the same, except for the very last byte. And then in the tweak, the difference, so this part of the delta, the third byte, is here. So 4 bits of the minutes, and then 4 bits of the seconds. And now if those are the same, yeah? So if the difference here, the difference between the call signs, matches the difference in the time, then we get this pair with a difference delta in plaintext and tweak, and then we can run our attack. Yeah? So let's summarize what we need or what kind of messages we need for the attack to work. We need that the frequencies are the same, and that's we more or less assume that the frequency is constant in the ALE network. We need that the word counters are the same, but this is actually trivially the case, because we will start at word 1, right? So if you compare those two words, it will always be the same word counter. And then we need that the messages are sent in the same 60-minute bin. Yeah? So bin meaning that here the upper bits of the minutes are the same, and then you only have a difference in the last 4 bits of the minutes. And then the seconds modulo 4, so the last 2 bits of the seconds also must be the same, but here we just assume that the seconds will be distributed somewhat uniformly, and then it will just happen by chance. And then of course we need that the difference in the remaining time, so those 8 bits here, and then the difference in the call sign is the same. And this we also, it will happen at chance eventually if the network is large enough. And then based on this, and some more assumptions, for example, assuming how many messages are sent in the ALE network, we can compute that it will take roughly 2 hours to collect the data. And that's essentially it. But before we go to the question session, let me actually answer some of the questions that are maybe quite obvious. First, did we disclose this to NATO? Yes, we did. But we never got a reply. So we sent them our paper before we published it, but they never came back to us. And this also means that a lot of the very obvious and questions that we want to have answered, we actually don't know. So for example, we don't know whether NATO will replace half-loop with something else. I would like to know, but sadly we don't know. And one other kind of obvious question is, why not just use AES? Yeah, because AES is such a well-studied cipher. Why not use AES? Why design this new half-loop cipher, which is just a mock-up version of AES essentially? And again, it's a good question. I don't really know. The obvious reason, so to say, is that AES blocks are too big. Yeah? In high-frequency radio, you only have a quite limited bandwidth, so you can only send very small blocks. And maybe that's why they designed this small-scale version. But actually, there are ways to use AES even for smaller blocks. You can use something like counter mode and then maybe add a actual authentication. But okay, that's just what I did. Yeah? Okay, so that's it. Here are some of the graphics, maybe to simulate some questions. If you don't want to ask a question now, or you're watching the recording or whatever, feel free to contact. I'm very happy to talk, and that's it. Thank you.
Thank you, Lucas. If you would like to ask a question and you're in the room, please line up at the microphones. If you're online, please put them in the according channels in IRC, and we have the first question going to the internet. Signal Angel.
Hello, and thank you for the very interesting talk. We have a question from the internet. You seem to have success using established methods against a contemporary military cipher. Do you know if military practices peer review to strengthen their ciphers? I also noticed that one of the co-authors on the paper looked like a military university. Would you say civilian and military researchers are working closer together now than 20 years ago?
Okay, so that's, I guess, more than one question. So maybe the first one was whether there's peer review going on, and well, I guess it depends how you define peer review, but for academic ciphers, of course, that's exactly what's happening, right? If you want to design a new cipher, you send it to a well-established conference or journal, and then someone else will have a look and give comments. But for this, I don't think that there was any kind of peer review. So this standard is just there. Of course, I don't know whether there's some internal peer review going on. I would hope so, but also then I would hope that they would have identified the weakness, but okay. And then I forgot what else there was, whether there's a closer collaboration maybe between military and
yes,
or whatever.
The question was whether there's closer collaboration between military and civilian.
Of course, I cannot really judge, but like I said, we told them, we sent a message, they never got a reply, so maybe that's more of a no, but of course I'm not going on, I don't know what's going on elsewhere. But again, maybe, like I said, the last question I answered already was, why not just use AES? I would argue that there's no really, at least in crypto, not really a need to have specific ciphers, because a cipher used in the general public should be so secure that also the military can very comfortably use it. Yeah.
Thank you. The microphone down here.
Hello, thank you for the talk. I wanted to know, in a real-world attack, is the tweak known or not?
Yes, so maybe let me go back to this slide. So this is the tweak, so T is the tweak, and then it consists mostly of a timestamp, and of course this time is known, right? You can just have a look at your watch, you know the time, and then the word counter, well, it starts at 1 and then it just counts up, and the used frequency is also known, because that's where you see the radio wave. Yeah.
Okay, thank you.
Thank you. Over here.
Oh, so first, thank you very much for the interesting talk. You were mentioning that you would need somehow around 120 minutes of data. And as far as I understood, this half loop is only used for handshake encryption. So is it likely that you would really, in reality, find 2 hours of handshake?
Yeah, so of course the 2 hours is, we assume that the messages or one such message is sent every, okay, I forgot the real number. I think it's like one message every 10 seconds. And then, of course, you can debate how many messages are really sent. but that seems to be a number. Of course, I mean, that just depends on how many communications going on, right? But then those 2 hours are not 2 hours worth of message if you put them together, but just 2 hours that you actually have to wait. So that's...
Okay, so you say you would find this in 2 hours?
2 hours, yes.
Okay, thank you. If I may...
Thank you. Then we have one question over there.
Okay, so I'm aware that there are some attacks on when you have access to related keys on AES normally,
Yes.
right?
Yes.
So, first of all, the question would be, is this somehow related to the attack?
Yes, this is actually very similar, because essentially what you get by having this tweak, because usually the attacker can get somehow related tweaks, and now, I mean, what you're doing, let me quickly switch the slide here. What you're doing, sorry, wrong slide. What you're doing is you add the tweak to the key, and actually this is a very bad idea. In the very first paper, the paper introducing tweakable block ciphers, they say, okay, don't do this. Yeah? If you do this, you get security only up to essentially to half of the bit size. Yeah? So there's actually a generic attack that will just work because you XOR the tweak here. And the reason essentially, as you said, now you have something like related key attacks, and then related key attacks are super powerful, and then for AES actually there is something known. I think only for the larger AES versions you have like related tweak attacks, and those are similar. Yes.
If I may, one small follow-up question.
Yes.
So why would you imagine they designed this cipher like that? Because as I understand, this was known at the
Yes.
point when they introduced this.
Yeah, also like one of the questions I would like to know the answer, but I don't really have. I guess they just weren't aware of it. Yeah, I mean, just adding the tweak to the key is something easy that you can do, but if you then don't know that, maybe it's not a good idea. It might seem as like a good idea at first glance, but it's not a good idea.
You have a follow-up question here?
Thank you. So, although you said you will not talk about 48 and 96, so what would be your estimate on what would be the additional effort to also destroy these?
Yeah, so first we actually have, I mean, the thing I just said, that because you just XOR the tweak to the key, that's also something happening in half loop 48 and 96, so this already gives you like this generic attack. And then, like from the perspective of crypto, this is already, we as academia already would consider the cipher broken. But then, I mean, an attack with 2 to the 64 data complexity, it's not so practical, because that's more data than it will ever be encrypted with half loop. But I mean, in the second paper, we have some considerations on the larger versions, so some meter and middle attacks. But those are not practical, and I mean, it's hard to tell how much work you would have to put in. But I mean, in general, I would say don't trust them. Yeah? Even though they are not as badly broken, at least for now, as half loop 24. But maybe don't use them.
Thank you.
Thank you. And the internet has another question. The Signal Angel.
Thank you. The next question would be, how do they handle the case when the encryption happens at, for example, 11.03.03.998 and decryption happens at 11.03.04.001? So there are different seconds.
To be honest, I don't know, because I don't know too much about radio communication. But I mean, worst case, you try both, right? I mean, decrypting something with half loop is very fast, and because there's so much structure in the plaintext, if we go here, I mean, you know that there's this identifier here and then the identifier here, they must be the same, right? So you can just, worst case, you try both seconds or both values for the seconds, and then you see whether you just get gibberish or you actually get the value. But of course, you should be careful to, I mean, maybe if you do it twice, it doesn't really matter. But if you start to decrypt a couple of thousand messages and try to find out which one is correct, that's also not a good idea, right? Because then the attacker only has to, gets something for free, right?
Thank you. Over here.
Is this algorithm fixable, or is the fix just use AS?
Yeah, I mean, that maybe depends on the definition of fixable, right? So an obvious fix would be to just use many, many more rounds. Yeah? Of course, that would destroy this attack, but this generic problem that you add a tweak to the key is something you have to fix. There's something for this, right? If you have a tweakable block cipher, it's known in literature how you should do this, right? So there's something like the tweak key framework that you could use. But yeah, is it worth fixing it? I don't know. Maybe something like in general, the design of half loop. Taking the AES box is very good. Those shifts are a bit strange because you could just move them into the mixed column. But in general, the components are actually strong. Yeah? So this is a strong linear layer and a strong S box. But then the details matter. So if you want, you could fix it. But yeah, I don't think it makes a lot of sense to do so.
Thank you. We have someone in the microphone, standing up at the microphone on the back.
Yeah, there are some attacks that focus on the block size rather than key size. For example, Suite 32 on triple des.
Yes.
And this algorithm has a small block size. Do you think it is vulnerable to this kind of attack?
Yeah, exactly. You have to be very, very careful about small block sizes. Of course, because you have something. There's maybe just not enough material in the plaintext. Here you have to tweak, so if you do it right, you have something that changes, but still you need to be careful because suddenly, we talked a bit about differential cryptanalysis. There's, you would study how this difference propagate, also like even in the non-deterministic case, and usually you cannot really say too much, but for 24-bit, actually you could probably compute all of the DDT, so that's a difference distribution table. So that's a bit, let's say, awkward, because usually in symmetric crypto it's something you can never do for the full cipher, but here it actually might be possible. So if you really want to look into the security, like if you would fix a cipher, it's non-trivial. Yeah? You have to do some proper analysis to see whether this stays secure or not.
Thank you. Microphone on the right side. Yeah, go ahead.
Is anything known about the authors of this cipher? Might have been a donation by the NSA?
No, so as far as I know, but I don't really have any sources for it. It was more, the design came from the high-frequency radio community somehow. And then, maybe let me say, there's this...
that was not just a joke. There are plenty of donations for real.
Yeah, I know. But, what I want to say is, there's Schneier's law, right? Everyone can design a cipher which is not secure. Which is not secure, but you think it's secure. Yeah? So I would not blame it on the people designing the cipher, but the people specifying this cipher without, doing some proper analysis of it. Those, I think, are to blame. Yeah.
All right, and the microphone in the back again.
Hey, thanks for the great talk. Do you have any idea why they still use ECB instead of a different mode?
Maybe. Where is it? ECB. Using ECB is okay, yeah, because it's a tweakable block cipher, and this tweak, because the tweak changes for every, because you have this word counter in the tweak, and then also the timestamp. It's totally okay to use ECB, so that's not like a vulnerability. So that's makes it actually quite simple.
All right, over here.
Do you have a proof of concept for this attack, or would it be legally problematic to do this?
We have an implementation. So in the paper, there's a link to a GitHub, and there's an implementation. And we did it. So of course, we didn't eavesdrop on HF radio, but in a lab setting. So we generated this plaintext ourselves, and then we run the attack. And essentially, there are two parts of the attack. First, essentially do what I showed. So you find out these bits of the last round keys, and this took something like 2 weeks on a CPU cluster, which is not the news. So if you really want and you put a lot of money into it, you can get it down to like an hour or something. And then once you have this, you have to brute force the remaining keys, and that's a bit simpler because it's just a brute force attack, and then you can run this on a GPU, and I think that takes another 8 hours or something, and then you have it.
All right, checking again. No more questions in the room. So thanks a lot for the awesome talk to Lukas Stennis.